So study guide review. All right, so regarding these parts, so you need to know, I will ask you a question, maybe questions, like which of the following is the part of respiratory zone, which of the following is the part of conducting zone. Essentially all the way down to terminal bronchial, it's the conducting zone. Respiratory bronchial, alveolar duct, alveolar sac alveoli, respiratory. Okay, conducting all the way down to terminal bronchial. Starting from respiratory bronchial, it's respiratory zone. These processes, please don't mix them up. Okay, so ventilation, air to the lungs, gas transport in the blood, external and internal respirations, that's the gas exchange, external in the lungs, internal in the tissues. Now, this is basically the anatomy of the nose, and I want to highlight a few things. So, ethmoid bone is the roof, maxilla and palatine is the floor. Which parts represent the external nose? Well, just like part like external nose, you know. Now, nose regarding to respiration. Warming up, cooling down, humidifying, filtering out the stuff. Okay, does that make sense? Speaking and sensory. Well, duh. Resonating chamber and olfaction. Epithelium. Please know your epithelium. In the nose, it's pseudostratified columnar ciliated. Function of cilia is to move mucus. Okay? Regarding the nasal secretions, what you need to know. Nasal secretions contain lysozyme, immunoglobulin A. And that's about it. Lysozyme is probably most important, is antibacterial. Okay? Conchae and meatae. The function of these two is to, remember, conchae are the folds and meatae are like grooves between them. Increase the surface area for more efficient heating up, cooling down, humidifying. Function of the perinasal sinuses, production of mucus, and resonating chambers. Perinasal sinuses to know frontal, maxillary, sphenoid, and ethmoid. Rhinitis and sinusitis, inflammation of the corresponding sinuses or nose. Does that make sense? Are we clear? It's basically like inflammation of the sinuses, sinusitis. Inflammation of the nasal cavity, rhinitis. We're good? Again, please just, like be able to say, if I ask you, which of the following parts is not a part of the internal nose, you have to say it like pick something like ala, okay, or the bridge, or the philtrum, right? And please know which structures make the nasal surface, increase the surface of the nasal cavity. Meatae and conchae. I cannot stress it enough. Pharynx. So for the pharynx, know which part is respiration only, nasopharynx, and know the epithelium. So the stratified columnar ciliated is in the nasopharynx, and stratified squamous in oropharynx and laryngopharynx. We're good? Now, larynx, remember that it starts at the laryngopharynx, opens into the trachea. The functions of the larynx. What are two main functions of the larynx? Voice production and keeping food and air separate. Superior and inferior portions of larynx. Superior is stratified squamous. Inferior is pseudostratified columnar. Okay. Thyroid cartilage forms Adam apple. The function of epiglottis, separation of food and air. Specifically, it closes the larynx during swallowing. You have to be able to recognize that statement as well. Am I clear? Closes the larynx during swallowing. Epiglottis. And it's elastic cartilage. The difference between vocal and vestibular folds. Vocal folds produce sound, and vestibular folds, sorry, I have to remove the keyboard. It's much more convenient without it in front of me. And vestibular folds open and close glottis. So far, we're clear? So, functions. Difference, well, how do we make sounds? So that's vibrations of vocal folds. Sound pitch is determined by the length and tension of the folds, and loudness by the velocity of air. So pharynx, oral nasal cavity, sinuses are all resonating chambers. Valsalva's maneuver. Okay, now I have no intention to describe it here. Remember, glottis is closed. Air accumulates in a thoracic cavity, increases intrathoracic pressure, that increases intra-abdominal pressure and stabilizes the trunk. Okay? Good? Make sense? Parts of respiratory system that are connected by trachea. Larynx and bronchi. Layers of the tracheal wall, please. Mucosa, submucosa adventitia. Which one is not there? Muscularis. Okay, so there's no real layer of muscles. Epithelium and mucosa, pseudostratified, columnar, ciliated. The function of the trachealis muscle is to cough. It contracts, producing cough. Okay, so trachea, you know the branching. Trachea branches into the primary bronchi direct the air into the lungs. Primary bronchi branch into the lobar bronchi direct the air into the pulmonary lobes. Segmental bronchi direct the air into the bronchiopulmonary segments. Bronchioles are branches of the bronchi. Conducting zone ends at the terminal bronchiole. Respiratory zone, bless you, starts at the respiratory bronchiole. Bless you. Conducting zone, the last element of conducting zone is terminal bronchiole. The first element of the respiratory zone is respiratory bronchiole. Structural changes. Less cartilage, more connective tissue, more smooth muscle. Structures of the respiratory zone. Respiratory bronchiole, alveolar duct, alveolar sac, alveoli. Alveolar sacs, physiological gas exchange. Structures that form respiratory membrane. Endothelial cells of the pulmonary capillary, simple squamous cell of the alveolus, and basement membrane between them. It should be thin for efficient gas exchange. Type 1 alveolar cells, simple squamous. Type 2 alveolar cells, simple cuboidal, produce surfactant. Alveolar pores connect alveoli, allowing to, equally distribute pressure, air pressure in the alveoli. Stroma of the lungs, connective tissue that surrounds the lungs on the outside. Costal surface, the surface that faces the ribs. Pulmonary arteries enter pulmonary veins, leave nerves, everything enters the lung at the hilum. Right lung's bigger, has 3 lobes, left lung has 2. Fissures divide lungs in the lobes. Bronchopulmonary segments are the smallest parts of the lung, supplied by segmental bronchi, can be surgically removed. Pulmonary circulation is the part of pulmonary circuit, and it collects the oxygen in the lungs and delivers oxygen-rich blood back to the heart. Bronchial circulation supplies the blood to the lung tissue directly. Okay, it's minimal. Bronchial arteries supply lung tissue. Bronchial veins drain in the pulmonary veins. Parietal pleura lines the walls of the pleural cavity, while visceral pleura lines the lungs. Space between the parietal and visceral pleura is pleural cavity. Fluid, it fills this space. During inspiration, air goes into the lungs. During expiration, goes out of the lungs. Intrapulmonary pressure. Pressure in the lungs, in the alveoli. It is lower than atmospheric during inspiration and higher than atmospheric during expiration. Zero respiratory pressure is the pressure that equals atmospheric. Positive, the pressure that is more than atmospheric. Negative, the pressure that is lower than atmospheric. Intrapleural pressure is the pressure in the pleural cavity. It is negative relatively to the atmospheric, and it's lower or negative to the intrapulmonary. It is negative because of the elastic recoil of the lungs and expansion of the thoracic cavity. If the fluid accumulates in the pleural cavity, that increases pressure on the lungs and may lead to the lung collapse. Transpulmonary pressure is the difference between intrapulmonary and intrapleural. Okay? Its function is to maintain lungs inflated. Okay? The bigger the intrapulmonary transpulmonary pressure, the bigger the lungs. Atelectasis is the lung collapse, usually due to the obstructed bronchioles that prevents the normal ventilation of the lung, which then decreases the pressure in the lung and leads to the collapse of the lung. So in atelectasis, intrapulmonary pressure is basically equal to intrapleural, and they both are less than atmospheric. Pneumothorax is the damage to the pleural cavity, which leads to the establishment of the atmospheric pressure in the pleural cavity. Okay, and the treatment is to reduce the pressure in the pleural cavity, to suck the air out. Does that make sense? So in pneumothorax, the intrapleural pressure equals atmospheric, and that leads to the lung collapse. When volume of the lung increases, pressure in the lung decreases, and vice versa. During inspiration, diaphragm and intercostal muscles contract. The volume of the thorax increases. The pressure in the lung becomes smaller than atmospheric, and the air flows in the lungs. So transpulmonary pressure slightly decreases. Intrapulmonary and intrapleural pressures decrease during inspiration. When we expire, diaphragm and intercostal muscles relax, volume of the thorax decreases, lung pressure becomes higher than atmospheric, airflow out of the lungs. Transpulmonary pressure slightly increases, intrapulmonary pressure increases, intrapleural pressure increases. How does airflow depend? So airflow follows the pressure gradient. Air flows from high pressure to low. Airway resistance prevents the flow. Airway resistance is insignificant because the lumen is huge, and lumen cross-section of the bronchioles progressively increases as we move towards smaller bronchioles. The mid-sized bronchi demonstrate the highest resistance. Resistance in terminal bronchioles minimal because diffusion of the respiratory gas out of the bronchioles into the blood starts to play a role. I'm going to stop for a second. Any questions so far? Role of surfactant is to reduce the surface tension. Type 2 alveolar cells produce it, and surfactant consists of water, protein, and lipids. So when alveoli inflate in inspiration, surface tension increases. When they deflate, it decreases. So if surfactant production is abnormally low, surface tension becomes really high, and it's really hard to inflate the lung, and it will collapse after each breath. Lung compliance shows you the change in the lung size at the given change of pressure. Okay, that's lung compliance. So the higher the compliance, the more lung will inflate at the given change of pressure. So basically, at the high lung compliance, the lung is much easier to inflate, and at the low lung compliance, lung is much easier to deflate. Lung compliance is reduced in restrictive pulmonary diseases like pulmonary fibrosis. May also be reduced by the conditions like scoliosis or ossification of the costal cartilage. Anything that reduces the capacity of the lung to expand. Okay, let's talk about the volumes. Tidal, normal breathing. Inspiratory reserve, amount of air that you can inhale on top of your normal tidal respiration, inspiration. Expiratory reserve, amount of air that you can expire after the normal tidal expiration. Residual, amount of air that is always left in the lungs. Forced expiratory, basically it's amount of air that is exhaled during a certain period of time forcefully. Capacities, total volume of the lung. Vital, everything except residual, total volume of the lung minus residual volume. Inspiratory capacity, tidal volume plus reserve expiratory volume. Functional residual, residual plus reserve expiratory. Forced vital capacity, the amount of air that can be forcefully expired after the full breath. So please know these 10. I will not ask you about any other except for these 10. Am I clear? Yes.
Can you go through and write them on the board or something so that
That's the lung. It's your normal breathing, tidal volume. That's the amount of air that is always left in the lung. This is reserve, or that's your expiratory reserve volume. That's your inspiratory reserve volume. That makes sense? This whole thing is the total lung capacity. This part is vital lung capacity. This is functional residual volume. And this is inspiratory capacity. Now, my best suggestion for this, just draw it. And it will make perfect sense. Now, forced expiratory and I'm sorry, forced vital, they are dynamic measurements that include time. So it's timed expiration to diagnose the obstructive pulmonary disease. Obstructive and restrictive diseases. We good? Or you got it? Let me know when we can move on. So obstructive and restrictive diseases. In restrictive diseases, your ability to just expand the lung is decreased. In obstructive, the resistance of the airways is increased due to the constriction or accumulation of mucus. So forced vital capacity decreases in obstructive, stays unchanged in restrictive. Minute ventilation, amount of air that reaches the lungs in 1 minute. That's it. No. Sorry. The amount of air that is inhaled in 1 minute, not reaches the lung. So if your tidal volume is 500 mils and you take 20 breaths a minute, it accounts for 10,000 milliliters, your minute ventilation. It does not represent the amount that reaches alveoli. Alveolar ventilation rate is the number of breaths per minute multiplied by, bless you, tidal volume minus dead space. Okay. So if I provide you with the respiratory rate, tidal volume, and dead space, you should be able to calculate alveolar ventilation rate or minute ventilation. The formulas are only lectures, and we did the little question on the quiz about it. Now this one, rapid and shallow will deliver less air than deep and slow. Non-respiratory movements, look, match the description with the movement. Okay, which of the following is sneezing? Now Dalton's law states that the total pressure of the mixture of gases is the sum of individual pressures for each gas. So the partial pressure of the gas, does that make sense? Yes. The pressure of the mixture of gases is the sum of individual pressures of each individual gas. Okay. So that's Dalton's law. The Henry's law is that the concentration of a gas in the fluid is proportional to its partial pressure over the fluid. The higher the partial pressure of gas in the air, the higher its concentration in the fluid. The higher the temperature, the lower the solubility. Now, few things. Remember that in the lungs versus the atmosphere. So in the lungs you have higher CO2 and water and slightly lower oxygen and nitrogen than in the air. Does that make sense? Or you can say, we have higher proportion of CO2 in the lungs, so higher proportion of water in the lungs. I'm not going to ask numbers, but higher or lower, you should be able to operate. Explanation: gas exchange, CO2 arrives into the lungs from the blood. Structural features are associated with gas exchange: the surface and the thickness. Okay? High surface and very thin membrane, they enable a very rapid gas exchange. If there is fluid in the lungs, respiratory membrane becomes thick and edematous, okay, and respiratory gas exchange decreases. In emphysema, the total surface area decreases, so the efficiency of the gas exchange will go down. Does that make sense? Now, this 4. Today's questions on external and internal respirations should not cause any problems. Okay, external respiration again happens where? Come on, where? Huh? Alveoli. Internal in the tissues. In external respiration, oxygen goes where? Huh? To the blood. In internal, to the tissues. CO2 in external goes where? CO2 in external goes where? Alveoli. In the internal? Nope, to the blood. CO2 goes to the blood. So, gas always go from which pressure to which pressure? High to low. So if I ask you, what is the pressure relationships for oxygen in the internal respiration, what do you say? Internal respiration, oxygen. Give me pressures. We have 2 pressures in the internal. Where? Blood and the tissues. What is the relationship between these 2 pressures? In the internal respiration for oxygen. Higher in the blood and lower in the tissues, because in the internal respiration, oxygen goes from blood to tissues. What is the relationship for pressures of CO2 in the external? Perfect. CO2 pressure in the external respiration is higher in the blood than in alveoli. Does that make sense? If you need, draw the scheme. Totally fine with me. Okay? Does that make sense? Now this is practice, practice, practice. Perfusion and ventilation of alveoli. If alveolus has high oxygen concentration, what happens to the arterioles that lead to that alveolus? Dilate. Low oxygen constrict. If alveolus have high concentration of CO2, what happens to bronchioles that lead to that alveolus? Dilate. And if it's low CO2, constrict. There you go. Okay. So we've got this. What carries oxygen in the blood? Hemoglobin. Well, hemoglobin, red blood cells carry it. Does plasma carry something? Just a wee bit. Yeah, just a tiny wee bit. Yeah, 1.5%. 4 oxygen molecules per hemoglobin. Hemoglobin saturation, percentage of molecules that it carry versus full capacity. Oxyhemoglobin, where are you going to find it? Okay, where is hemoglobin? In which cells? Red blood cells. Red blood cells are where? In the blood. Okay, so where are you going to find hemoglobin first and foremost? In the blood. Oxyhemoglobin in which blood? Huh? From lungs to tissues. Deoxyhemoglobin from tissues to lungs. There you go. Okay. Cooperative binding, you just answer. each next oxygen binds easier. Hemoglobin dissociation curve reflects the relationship between partial pressure of oxygen and hemoglobin saturation. When oxygen partial pressure is high, with a change in oxygen pressure, hemoglobin saturation changes dramatically or not. High concentration of oxygen. Not. That's here. Okay? When it decreases, hemoglobin starts to oxygen starts to unload. During normal resting state, what percentage is unloaded? 25, yeah. What's the importance of venous reserve? Oxygen that is remaining oxygen that is bound to hemoglobin. What's importance? If we get suffocated, it's about 2 minutes for the brain function. Okay? Does deep breathing increase hemoglobin saturation? No. Why? Because binding saturation doesn't really change at the high oxygen concentrations. It's already 100%. You cannot saturate it more. Does hemoglobin saturation change significantly? Not changes. Significantly when somebody travels into areas with high altitude? Not really, because there is very little drop in saturation even if pressure of oxygen decreases. What happens to hemoglobin saturation in tissues when we exercise? Saturation decreases in the tissues, and that means what increases? Unloading. Does that make sense? Since oxygen concentration in the tissues goes down, it means hemoglobin saturation will decrease, and it means it's just going to unload more. Again, don't forget about the forest. I'm talking about the trees, but don't forget about the forest. When oxygen concentration in tissues goes down, hemoglobin readily gives oxygen to the tissues to kind of make sure that there's enough. Temperature. Which temperature increases unloading? Elevated. Which CO2 increases unloading? Elevated. How we call this effect? The big guy. Bohr. What are these characteristics of metabolically active tissues? In metabolically active tissues, temperature is elevated. Please speak up. Elevated. pH decreased. CO2 increased. Oxygen decreased. Yes, very good. In the lungs, temperature lower than the rest of the body. pH slightly higher. Basic. CO2 decreased compared to the tissues. And oxygen through the roof, yes. So, all these factors increase unloading, and these factors basically decrease unloading or increase loading. Does that make sense? Hypoxia. I deliberately made it a little larger. Anemic. Quickly. Not enough red blood cells. Ischemic. Of what? Blood flow. Not enough blood flow. Histotoxic. Because of histotoxic. Some kind of a poison, toxin, yes. Blocks the cell respiration. Hypoxemic. Yeah. You're being strangled. Okay. Carbon monoxide binds to iron and prevents oxygen from binding. Carbon monoxide binds stronger. How is CO2 transported in the blood? Dissolved in plasma, bound to heme in hemoglobin. Sorry, not to to protein in hemoglobin, forming carbaminohemoglobin. Yes, it does bind to hemoglobin, to the protein part. Remember, CO2 binds to the protein part, forming carbaminohemoglobin, and in the form of bicarbonate. Reaction between these two happen fast because there is an enzyme, carbonic anhydrase, in RBCs, but no such enzyme in the plasma. Reaction product, carbonic acid. Carbonic acid dissociates into the hydrogen ion and bicarbonate. Bicarbonate from RBCs enters plasma, chloride shift. What's the role of bicarbonate in plasma? Some kind of a system. Buffer system. Hydrogen ion in RBCs binds to which protein? In red blood cells. In red blood cells. Hemoglobin, and in a plasma it binds to albumin, the most abundant. Hydrogen binding to hemoglobin changes the shape of hemoglobin and increases oxygen unloading. In the pulmonary capillaries, hydrogen ion and bicarbonate ion do what? Bind to each other, forming carbonic acid. Carbonic acid in pulmonary capillaries splits into water and CO2. Everything goes backwards. Hydrogen ion bound to hemoglobin in the pulmonary capillaries unbinds from it. How does bicarbonate buffer system respond when blood pH decreases? Decrease means more acidic or less acidic? More acidic, meaning more hydrogen ions. These extra hydrogen ions will bind to bicarbonate. Now, if blood pH increases, means not enough hydrogen ions, carbonic acid will dissociate. Hyperventilation, how does it change blood pH? Speak up. Okay, increases, meaning it becomes less acidic because you exhale CO2. Hypoventilation decreases and makes it more acidic. What pH will increase the ventilation rate? Go ahead. When you start breathing more actively, what do you exhale more? CO2. How does it change pH? Makes it higher. Your acidity goes down. I told you, pH thing. So, if increased ventilation rate increases pH, which pH stimulates the elevated respiration rate? Low pH, ventilation, CO2 is out, higher pH. Does that make sense? Okay, so this you need to look through.
So low pH is
Acid.
so deeper.
You start to breathing faster. You exhale CO2. CO2 is acid as well. So you exhale acid. What happens to pH when you exhale acid? It goes up. The problem is that you have a wrong association of pH and acidity. Low pH means what? Acid or base? Acid. So if you have low pH, you have a lot of acid in the blood. Does that make sense? When you low pH stimulates respiration, what do you exhale when you respire? CO2. CO2 is acid as well. So you exhale acid. You take acid from the blood and get it out. As you take acid from the blood, what happens to acidity of the blood? When you take acid from the blood, what happens to acidity? Acidity goes down and pH goes up. Okay? So review the pH scale. Ventral respiratory group. Okay. Normal rhythm. Dorsal respiratory group. Transitions between normal rhythm, between inhalation and exhalation. Sorry. Okay, transition. Brain freeze. Adaptations to exercise. Pontine respiratory centers. They communicate with dorsal and ventral respiratory group and responsible for adaptations in speaking and singing. Chemical factors that are most important in the regulation of respiratory activity. The most important is concentration of which gas? CO2. Second, pH. O2 is the least important. Why? We have venous reserve. Remember, we have a lot of oxygen bound to hemoglobin. So, high CO2 in the blood, how does it change respiratory rate and depth? High CO2 in the blood will increase. Again, low pH will increase. You exhale acid. And when you hyperventilate, what happens to CO2 in the blood? It decreases. What happens to pH? Increases. Very good. Because that's chemistry. That's chemistry. Oxygen. If we get to this point, oxygen elevated. Now, tricky question from my side. Elevated oxygen, how will it change rate and depth of breathing? Say it again. Elevated, hypothetically, elevated oxygen in the blood. Although it never happens, but decrease. Does that make sense? Well, if you have a lot of oxygen in the blood, you don't need to inhale anymore. Does that make sense? And if you not have enough oxygen, you really need to inhale it. Does that make sense? Slight changes. No influence on the respiratory activity because you have venous reserve. Hypothalamus. Emotional respiratory movements like gasping. We can control breathing voluntarily. We can hold the breath. But normal breathing will be reinstated when CO2 is very high. Irritant reflex. Sneezing, coughing. During exercise. Why? So it's a neural factors. Neural factors. So it's input from the proprioceptors, okay? Activation of the motor cortices and conscious appreciation of the fact that you're about to do exercise, okay? Muscle switch to fermentation during heavy exercise because of insufficient blood flow, not because of insufficient ventilation, okay? Respiratory system fully sufficient. High altitude may lead to pulmonary and cerebral edema due to the increased pulmonary flow and cerebral flow because of the low oxygen. Acclimatization of high altitude, minute ventilation increases, red blood cell amount increases. So technically speaking, minute ventilation is a short term, RBC amounts long term. Chronic bronchitis. Well, I mean, in the long term, if you go there for a week, minute ventilation will be increased all the time and RBCs will go up. But if you go there for 5 hours, the only thing that's going to change is your minute ventilation. This is why we call it a short term. Chronic bronchitis is obstructive, inflammation of the respiratory passages, treatment, anti-inflammatory mucolytics. Emphysema obstructive, asthma obstructive, mostly allergic. Asthma is reversible. Cystic fibrosis, chloride transport protein defect leads to accumulation of the mucus. Respiratory passages and other ducts are clogged. Treatments for the respiratory component: mucus thinning drugs, inhalation of the saline, also called tapping, dislodging of the mucus. Antibiotics necessary because mucus traps bacteria. Tuberculosis, infectious disease, cough, fatigue, night sweats, treated with antibiotics. Lung cancer, #1 cause of death from cancer. Underlying cause: smoking. Treatment options: early diagnostics, radiation surgery, checkpoint inhibitors. Late stage diagnostics, prognosis is poor. Fetal lung is inactive, filled with fluid. Gas exchange occurs at placenta. Thoracic wall becomes less flexible, calcified. Respiratory passages usually have more mucus and less cilia. Lungs become less elastic. Alveoli becomes larger. That's it.